So let's proceed to the second talk on Nobel Prize in Chemistry. Now, I would like to invite the second speaker of the day, Professor Ramakrishna Ji Bhat, professor in the Department of Chemistry at IISER Pune, obtained his PhD from ISC Bangalore and postdoctorate from Simon Fraser University, British Columbia. His research interests include organic catalysis and synthesis. Now, I would like to invite Professor Ram to take over this. We welcome you, sir.
Thank you so much. Um, First, let me share the screen. Just see that whether you will be able to see it. I think Nixon, you are still presenting, I guess. Okay. Uh, yes, I thank you so much. Okay. Let me see whether you are able to see the screen.
Yes, sir. Screen is visible now.
Okay, just a minute. Okay, where for me, where I should see my screen. Okay. Do you see the screen fully or
Sir, we can see the infinity screen, right?
you are able to
Equals.
see?
Yes, sir. Now we can see.
Okay, just a minute. Huh? I'm sorry. It's not very comfortable for me. Okay. Um, is it a full screen mode? Okay. Let me arrange a bit so that I can speak without any problem. Okay. If you all can hear me very clearly, am I audible to all of you? One of you can say yes, so I can go ahead. Okay. First of all, I'm very, very delighted to be part of this Nobel Evening Lectures series. I'm very happy to be part of this because I'll be talking about Nobel Prize in Chemistry. I will try to do a bit of justice because it's a huge, vast ocean, the chemistry itself, and in that asymmetric catalysis, and in that there is another one called a C, you can say organo catalysis in the field of chemistry as an ocean. To begin with, let me thank Science Club for the wonderful plan and active involvement. I can see that many students are still there. They are at the back of back at home. They are not in the campus. Some of them have come, but many of them are still, they have not written. But I still feel so great in spite of all the problems, hurdles. They are interested in arranging such kind of events. I think it is worth appreciating. Students, really keep it up. And students told me that this is a more of a public lecture, and I do understand that because students from a different background, even the school students, even the faculty and the staff from different background are interested to listen to this. So let me make it as simple as possible and try to make it a very general lecture. I will not really go into the depth, but I'm sure you will understand at the end of the lecture that why organocatalysis. So all of us know that this year's Nobel Prize has gone to Benjamin List and David Macmillan. So the David Macmillan, by Scottish origin, but entire career he worked in USA, and the Benjamin List, a German, worked very briefly in USA and then came back to Germany. And they got the Nobel Prize for the development of asymmetric organocatalysis. What is so big deal about the asymmetric organocatalysis? So to begin with, let me start off with a quote. There is no science for the sake of science, no art for the sake of art. They exist for the sake of society, for the ennoblement and exaltation of a man to enrich his knowledge and to provide his material or her material comforts. So science, at the end of the day, it's good to do for the sake of science, but at the end of the day, it should reach society. And that's exactly the Nobel Prize Foundation said that this Nobel Prize is given for the great contribution which has really reached to the society. So what is so big about this organocatalysis? Why are they in news? What is so special about it? So the most important thing is these Nobel laureates, they have worked very significantly, remarkably, and their seminal research work in the year 2000 really made a foundation stone, or you can say that it constituted or conceptualized the research area of organocatalysis. And it became one of the pillars for the catalysis field. And it became a third pillar for catalysis called organocatalysis or asymmetric catalysis. What the Nobel Prizes Foundation said that very beautifully, very aptly, they said they have come up with a new tool for finer chemistry. And this is the image that I have taken from the Nobel Prize site. You can see that the older tools where you can get some kind of stool, bar stool, and chairs, and very precisely, asymmetric organocatalysis can give you a handedness in the molecule. You can beautifully, precisely make the molecules, and hence they called it as tool. So let us see very carefully why this is tool. And to dwell into asymmetric organocatalysis or organocatalysis, I need to go back to history. I need to go back to some extent to the nature. We have an intimate relationship with molecules. All humans, animals, birds, you take anybody, including the microorganisms, we have an intimate relationship with molecules. You can see that we are all made up of molecules, and the nature is full of molecules. We are surrounded by molecules, and we are in the molecules. And I have seen here just now Professor Abraham's talk, Nixon. He talked about the taste and the smell and all these things and the touch. And we have five senses when we say, we talk about touch, whether you talk about seeing, whether you taste, or you smell, or you hear. All these five senses have to do with a lot of interesting mechanisms, and obviously molecules are there. And then we can go back to the philosophy of 2000 years, from whether it's the Indian philosophy or the Chinese philosophy or even the Greek philosophy. So we talked about the five elements. Greeks talked about the four elements. So what we talk about, the Agni, the fire element, water, the Jala, and the earth element, which is Prithvi, or we can say the air element or the Vayu Tattva, or the final one, they say Akasha, or the space, which is missing in the Greeks, whereas Indians had this concept, even the Chinese, yin and yang philosophy. And the Indian philosophy and the Chinese philosophy greatly believed that what is there in the nature, that is there in you. You are, as a human being or animals or the birds, are the reflection of the mother nature. So hence, everything is within you, say Brahmanda and the Pindanda. So hence, it's very beautifully connected philosophically as well as scientifically. If you see the holistic nature, we are all made up of nature. And if you see the reductionist nature, you can see atoms. Atoms make the molecules, molecules make the body, and the whole molecules make the biopolymers, which are there in the body, and these are the nature, and we talk to each other. And small molecules make to the biopolymers, and they are the building blocks for the life. So now we have inseparable bonds with the molecules. As I said, we are made up of molecules, but in everyday life, we have to deal with a lot of molecules, but we do have an inseparable bond with the molecules in everyday life. Whether you drink a cup of coffee, caffeine is there. Whether you are eating an orange or a lemon, you have a vitamin C, you are eating the vitamin C. You are writing something using a pencil, you have a graphite. You are eating chips, a salt or the potato, the carbohydrate is there, sodium chloride is there. Water, the simplest molecule, which is a molecule. And you talk about mobile, anywhere, materials are there. And these change our mood. We feel good, we feel bad. But then can we say that we feel bad because of anything else? Again, you say, oh, this is something to do with the molecules. You talk about oxytocin, a love hormone. We talk about the dopamine, alertness, norepinephrine, serotonin, dopamine. You talk about anything which defines you. Or when you think something, these molecules are released, or then they release, you feel it. Like, for example, adrenaline. You feel a tiger, you saw a tiger, you feel afraid, or you feel like rushing. Molecules are generating in the body. So that means molecules are there everywhere, and they talk to you as well. Go to kitchen, you have molecules. Chemistry of spices. You talk about menthol, mint, menthol is there. Cardamom, you have a cineol. Cinnamon, you have a cinnamaldehyde. You talk about coriander leaves, decanoic acid, curcumin, turmeric. You talk about any molecules, you have organic molecules or molecules everywhere. It's not true that only organic molecules make up the living things. The inorganic molecules, whether it's simple salt like sodium chloride, potassium chloride, even they make your life. They are not lifeless. So when I'm talking today, like ion channels are there where molecules move in and move out. So brain needs the ions. So hence we are all made up of molecules, whether it's organic or inorganic. Today we'll deal with more of organic molecules and molecules that matter. So when I say molecules that matter, you can see over here a lot of organic molecules, whether you talk about propranolol, which is a beta blocker, whether you talk about analgesic, whether you talk about esomeprazole. Some of you might have popped up the pill called omeprazole, which is also called esomeprazole if it is a one single enantiomer. So you have antiviral drug, you have antibiotic, you have anticonvulsant, you have antidepressant. You talk about anything, you have some organic molecules as a medicines. But one thing is common over here. Please see with a full attention. All these molecules have a chiral carbon, and they all are chiral in nature. When I say they are in chiral in nature, I'm sure all the students know a chiral carbon, one single chiral carbon can have two isomers. We call them as two enantiomers. So now this carbon has four different groups. They are asymmetric in nature. There is no plane of symmetry. Hence, there is no symmetry. Hence, it is asymmetry. It is not symmetric. Hence, it can exist in two enantiomer as a mirror images. And these molecules matter because they save our life. So why should we study the past? So there is a famous statement by Confucius. I think some of you have heard about Confucius. Study the past if you would define the future. So today's Nobel Prize winners that I'm talking about, they beautifully, thoroughly studied the history. And that's the reason in the scientific journals, we always give a back citations. We always give back citation because Newton said we're all standing on the shoulders of the giants. We don't do everything from the scratch, right? We always do incremental science. We keep adding, and then we go up. So before we go further, the history is so beautiful. Let me take few minutes to talk about the history. So then I would build on the story. So let us go on a voyage. Let us go back to 200 years almost. Let us go around 1800. A great person, John Baptist Byatt. Somewhere in 1855, Byatt was so much interested in a lot of physical properties. See, he was synthesizing a lot of molecules or synthetic molecules. Tartrates, he was talking about dealing with the tartrates. And then he used tartrates and he put it under the polarimeter. I think all of you have handled the polarimeter. I don't know whether, say, digital polarimeter some of you have seen, and also undergraduate lab you might have seen the old-fashioned polarimeter where you can turn and you can see dark and light. That it rotates a plane polarized light. Uh, the Byatt did a seminal discovery. I can say that in 1855, somewhere in 1800, you can say it started. He could make up the solution of organic chemicals, especially tartrates, that rotated the plane of the polarized light, or plane polarized light, we say, to the left and the right. And he proposed that these molecules of a same compound could exist in two different forms. And he called these as a left-handed as well as right-handed molecules or forms. These molecules were described as optically active. Remember, so one thing is very interesting. Van has not even proposed carbon is tetrahedral, the first Nobel laureate. Here in 1855, we are talking about a molecule it is having right-handed and left-handed molecules. And his compatriot, Louis Pasteur, another great man, great scientist, biochemist, chemist, you can call him anything, whether it's a vaccine, anything you talk about him, I think we should have big salute to Louis Pasteur. Around same time, 1880, he was approached by wine industries because wine industries had a big problem. If you keep the wine for a long time, we say a wine gets better with the vintage. But the problem was, if you keep the wine for a long time, the crystals used to deposit on the cork as well as the bottom. So it was not very easy for the people to consume, and it was not easy for the people to purchase. The French companies reached or approached Louis Pasteur and they asked him, "Bonjour, could you please help us? We have a problem with these crystals. We don't know what it is. Is it possible for you to help us in removing this?" Louis Pasteur, reading the history very well, he knew what John Baptist Byatt did painstakingly. He looked into the solution of the wine and he really, working so hard, removed the crystals, and these two crystals were of two different forms. And again connected to history, Robert Hooke or Anthony Leeuwenhoek, microscope. It was already there. So you just see how incremental science is happening. And the physics or chemistry or biology, or you talk about any subject, they're all interconnected or interdependent. So hence they helped each other. So now you can see beautiful crystals. They are like a mirror images. And then he called it as racemic mixture. In Greek or Latin, racemus means grapes. And the wine comes from the grapes. And he called it as racemic mixture. And then he separated them and he said, oh, they are again moving or rotating the plane polarized light in the opposite direction, clockwise and anti-clockwise. Now, Pasteur did a fantastic work or a great seminal work again and demonstrated that light rotation saw what he saw, what the Bayard saw, is linked to the physical shape of the molecule. See, remember, as I said again, I'm repeating, chiral carbon, this is something beautiful, okay? He says, or he believes, that these opposite plane polarized rotation is due to the shape of the molecules, means they are exactly opposite to each other. And he further showed that optical active molecule were not symmetrical. This is a very founding stone. So now chirality and stereochemistry, I think many students know about it. When I say chiralness, when I say chirality, when I say about handedness, in the Greek, chiral means hand. So chirality comes from the handedness. As we have two palms, which are mirror images, and they are mirror images, but they are not superimposable, right? So you cannot put one above other, they don't exist. So same way, if you take a chiral image, they will not. So biological significance of chirality is immense, right? So even the crepe can take a proper helix, a right-handed helix sometime, and the mother nature has chosen L-amino acid, D sugar. Exceptions may be there in certain bacteria, but then most of the organism, almost all animals, we are made up of L-amino acids, D sugars. And you can see the nucleic acid taking the helix. And because of the L-amino acids, proteins which coiled up like that of complex molecules, they take the right-handed helix. So they also become a right-handed because of the L-amino acids. So hence, a simple building block L-amino acid determines the chirality of the biopolymer or the protein or the carbohydrates we talk about, right? So hence, a chirality becomes a very, very essential. And what is so big deal about chirality? So as I told you, it is handedness, that's fine. And you can see everywhere there is a chirality if you see, observe carefully. If you have eyes to see it, you can see many things. Why it is so important? Why so important for the importance for the right-handedness or the left-handedness? What is so big deal about the handedness? See, a right hand will go forward for shaking another right hand. A left hand and right hand shake is not very convenient, which is not very easy. It is not very firm. You can see right hand shakes well, or left hand goes well. What makes us to be right-handed? In the audience, I'm pretty sure, or in the classroom, around 90 to 95% are right-handed. Very few are left-handed people. In India or the Asia or the Asia Pacific, almost like 95, 96% people are right-handed in nature. Very few are left-handed. In Europe, maybe 90. But large proportion of human beings are right-handed in nature. Sorry. Uh, can you see? Uh, Friends, can you see that
Ananta,
video?
Ananta someone.
Yes, sir, we can see.
Okay. Sorry for the disturbance. So let me get into my slide. It got misadjusted because of the disturbance. Sorry about that. So I was in a flow. That's fine. Sorry for the interruption.
It's all good.
You can see clearly now?
Yes, sir.
Friends, you can see clearly?
No, sir, now your screen is not visible to us.
You can see now?
No, sir.
Uh,
I think you have to share your screen again.
You have come out of presentation.
okay. I think, can you see that now?
Yes.
Can you see? Okay, sorry. I think I was trying to mute myself because nobody was muting someone. Okay, so let me continue with my talk. Sorry for the interruption. You can see over here, I think the screen is, if it is visible, you can see over here what I was trying to say, that handedness. Why handedness is so important? And what makes human beings, majority of the human beings, right-handed? It is any something, a code, a memory code. You can see a baby I have shown here in the extreme right, in the mother's womb, holding her right thumb, right hand, right thumb. And we are not alone. Even the apes, the great apes, almost like 75 or 70 to 75%, they are right-handed in nature. You can see that. And very few, 20-25% are left-handed. And the Canadian, or you can see in Canada, the narwhal, which has two tusks, but most of the time it just pushes only one tusk, and it is in the spiral nature. And this is a beauty. Another beauty you can see over here, the snails, the clockwise and the anti-clockwise snails, the spiral snails. And these spiral snails are again right-handed in nature. Most of the snails, majority are right-handed in nature. Why Mother Nature has chosen to be in one handedness? And you can see very clearly, I've shown B and C taken from an article. The clockwise chiral coiling snail shell, just like a handshake, they are coming so nicely and advantageous physical engagement for the benefit of the co-population. So hence they can mate easily. Look at the unlucky left-handed spiral snail. I've shown in this C. So right hand, left hand combination doesn't go well. Differently, chiral snail shells have physical disadvantage for the co-population. And this is a problem. And then this is something very interesting too. So if that I continue further, how special is chirality? As I said, this is a very common example that anybody gives. If I take a lemon or a limonene, which has two enantiomers or two isomers, if I talk about limonene or S-limonene, one smells like an orange, another smells like a turpentine or a lemon. And then if I take another molecule called Darwin and Novard, these two are again mirror images. One is a painkiller, another one is the anti-cough agent. So if you take about these sugars, equatorial, axial, these bonding even can change into cellulose or starch. So much beauty is there in the handedness or the chirality. So what was something, a drastic thing happened because of the chirality? So somewhere around 1960s, a shadow of thalidomide tragedy. Some of you might know it. That thalidomide as a drug was prescribed to pregnant women who used to get morning sickness, and especially in the first 3 months period, the pregnant women feel vomiting sensation or morning sickness, it's called, and doctors prescribed them thalidomide. And unfortunately, many babies were born with a vestigial arms, defected babies. Lots of babies you can see, armless babies. So at those days, people thought this is a witchcraft, or you can say this is like a magic, black magic. And then a lot of things went wrong, and they thought, okay, this molecule is having a problem, and they banned this molecule. The drug was banned. Then later they understood these molecules are existing as mirror images, and one molecule called R-thalidomide is sleep-inducing, which is good for the morning sickness, and the S-thalidomide, which is a teratogenic, which can cause a severe effect that you can see here, which can play around and which can do a lot of havocs. Then FDA came up with an idea that do a racemic switch, means come out of the racemic mixture, make one single enantiomer, make a drug enantiomerically pure, single enantiomer that we needed, the way Mother Nature does that. So this is something important. So just now I talked about limonene, just now I talked about this thalidomide. Why that happens? I think just now Nixon talked about the all the sensations and the sensory system. You can see we have receptors and enzymes, right? Certain places molecules act onto the enzymes active side. Certain time they go and bind to the receptors. The proteins are receptor. They don't catalyze any reaction, but they're receptor. We'll take here an example, a schematic representation. If I take the three-dimensional molecule here, a molecule is approaching the catalytic receptor, where you can see there's a pocket. A triangle will fit into the triangle, a square can fit into square, and a sphere can fit into the round area, that you can believe that circle area. I mean, this is a lock and key mechanism, just to give you an idea. It may not be exactly like that. Inducive fit theory as well works. Why only one enantiomer is bound to the by receptor? So hence, each protein, each molecule or enantiomer can bind to a specific receptor, and it can uh, elicit a certain response. Now, we need to make a one molecule very specifically. As I told you, chiral switch. Now, the onus was on synthetic organic chemist, or you can say medicinal chemist, that how do I synthesize a molecule, single-handed molecule? So Mother Nature makes a molecule so beautifully using an enzyme. It would make very easily one single enantiomer, almost quantitatively, exclusively. So now chiral switch, when I talked about, many medicines are sold as racemic compounds. So as I told you, if you go to the druggist and ask him omeprazole, he would give you omeprazole, which may be racemic in nature, and the price would be much more cheaper. If you go and ask him esomeprazole, it will be very expensive because that is only one enantiomer. If you ask the druggist, give me cetirizine for the allergy, and he would give you a one strip of 10 rupees, then it is a racemic cetirizine. And if you ask him the levocetirizine, it would be quite expensive because now labor intense work is there to synthesize a one pure single enantiomer. So that means synthetic organic chemists have to work around on the bench and just like nature, synthesize it by mimicking her. So I've shown you many molecules here. They had to go for the chiral switch. So now, not only thalidomide, there are many molecules which are important, whether it's a vancomycin, mycotoxin, sucralose, which is the artificial sweetener. You can see everywhere, as I said, chiral compound is there, chiral carbon is there. And you see the beauty of the mycotoxin, how big that molecule is, how many chiral carbons are there. And you need to make this entire molecule in one single enantiomer pure form. Vancomycin, whether it's a paclitax or anti-cancerous agent. But the problem is, why can't we take from the nature if some of them are available in the nature? For example, mycotoxin, vancomycin. But friends, the plants and the organisms will not give you enough medicine or enough molecules which can serve the millions of people. These molecules are working like the bridge between life and death. So you are cutting the trees which are maybe 200, 300-year-old tree to get few milligrams of these very useful compounds. Can we cut those trees? Is it enough? So hence we need to synthesize on the bench. So hence our journey starts. All of us know that catalysis becomes a very important thing. In the earlier days, synthesis is started from 1700. You can say Friedrich Wöhler's time organic synthesis started. Then slowly catalysis started. You know that Sabatier. Actually, catalysis started long ago. Berzelius is the one who started in 1850s. Then you know that almost like 14 Nobel Prizes have gone to catalysis. Such an important field. Why is that? Because almost like 35% of the GDP depends on the catalysis. Many industries, pharmaceutical industries, agrochemical industries, fine chemicals, polymers, perfume, fuels, you talk about anything, are dependent on the catalysis. All of us know catalysis. I don't need to define it. I've just shown here how it enhances the rate of the reaction without really being a part of it, but it is really enhancing the activation energy. And you can see that it is lowering the activation energy barrier, and reaction goes faster. And then it is so simple because there is atom efficiency there. So now catalysis is a huge field. And as I told you to begin with, asymmetric catalysis or organocatalysis became one of the third pillars of the catalysis. What are the other tools? The complementary catalysis are enzyme catalysis or the biocatalysis, the transition metal catalysis or metal catalysis or organometallic catalysis, and the last one, or I should not say last one, I should say the latest one or the third one is the organocatalysis. And the organocatalysis is the third pillar. And why it has emerged? As we know that enzyme catalysis, beautiful. Enzyme, a mother nature is having enzyme, and you take the enzyme, you isolate it, and use it to get the one of the molecule in pure form. Let us say we have reduced the ketone to alcohol in 99% enantiomeric excess. Fantastic. Now, transition metal catalysis. You take the transition metal catalysis or the complex, maybe which has a chiral ligand, but then the metal is in the center. Metal is necessary because we have a variable oxidation state. It can be a kind of bank for the electrons. It can give, it can take back. So if that is true, we can have the organocatalysis, we can have the metal catalysis, and many people have won the Nobel Prizes. You know that. We know very well that Knowles, I think if you can go back to the metal catalysis, if you have studied in the course, we have a lot of prizes have gone, whether it is Ziegler Meta and many places, metal catalysis are involved. And then that's one of the very important field too. And then organocatalysis. And you can see the beauty of organocatalysis is, as the word says organocatalysis, only you can see organic molecules here. You don't find metals and you don't find enzymes, and hence organocatalysis. And then what are the drawbacks and advantages? I will not dwell too much, but then limited substrate scope for the enzyme catalysis. You may not have all the enzymes, and you may not be isolate very easily. Purification may not be easy. Solubility may be issue. Access to one enantiomer only, because you have only one type of enzyme unless you make it. Hence, you have only one access to one enantiomer. Metal catalysis or transition metal catalysis, potential heavy metal pollution, possible toxicity, expensive. Many metals are rare, not abundant, but then you have to depend on that. Stability is an issue many times, though there are not true for all the complexes, but then many times you have to be very careful about the stability or the air sensitivity, or it can be tedious process. Hence it is sometimes a limiting factor too, even though they have contributed significantly. We can't take the credit away from the metal catalysis. But then comes the sustainable future, possibly sustainable future, because you use the organic molecules which are there in you, or which is there in the nature. Hence we call these molecules are chiral pools. They come from the chiral pool of Mother Nature. They are simple, they are small, extremely small, you can say. So 150 to 200 atomic mass unit, sometimes slightly more. But that is nothing compared to the large biopolymers like 20 kilodalton, such kind of proteins or enzymes. Inexpensive, non-toxic, because it's like a supplement that you're taking. You're taking the protein shake, you have amino acids, and same amino acid you use for the organocatalysis. No special condition needed, because it will not be killed by the water or the moisture. And the catalyst loading is a concern, but let us dwell more into this. And what is asymmetric organocatalysis is all about? Let us just quickly go to the fundamentals of this. Very quickly, organocatalysis I will talk about. Let us say you have a reactive intermediate, that's a carbocation, which is going to generate in the reaction medium. And it is reactive because it is going to react faster. Hence, it is an intermediate. It doesn't exist as a molecule. This reactive intermediate, based on your foundations in the first semester or even in the 12th standard, that it is a planar in nature. If it is planar in nature, you can expect the nucleophile to attack from both the sides. If it attacks from both the sides or both the faces, you would end up in getting two different molecules, L amino acids or D amino acid, or L compound, a D compound, or L isomer or D isomer. We can also call that R isomer or S isomer using the Kahn-Ingold-Prelog rule. So if that is true, how do I control the selectivity? How do I make it so enantiomer selective or enantiomer specifically that I'll get one molecule? How do I mimic the nature? How do I follow the nature to the large extent so that I just make one single molecule on the bench? So idea comes from the enzyme itself. Enzymes have an active site, or enzymes like a pocket. There is an active site pocket, there's a gully. If there's a small gully, not a big national highway, only a small vehicle can go there and come back, right? So now if I take this molecule and then I can shield the molecule from one side, the way I have shown here, a guarded, the one of the face is shielded because the molecule is shielded by another chiral molecule. And that chiral molecule will induce chirality, induce selectivity. If that is true, now you can see that from the left hand side, nucleophile cannot approach because this is too bulky, or a pocket or a shield, a catalyst wall is there. If that happens, you obviously don't find time. Maybe there are very small percentage may sneak through, but large population of nucleophiles would have to depend on the right hand side, which is the free side, and they would approach from the one side. And if that happens, you would almost get exclusively single enantiomer. But remember, it's not so easy, just the way I said it.
but this is the principle, right? So now let me start off with the pre-organocatalysis era. I would not say organocatalysis word was not known in the pre-organocatalysis era, but for the sake of understanding, let us start pre-organocatalysis era. So we must remember one great scientist, organic chemist. He is none other than Gilbert Stock. And why Gilbert Stock is so important for us? Gilbert Stock did a seminal work. If I take a cyclohexanone and if I treat with ethyl bromide, you would end up in getting usually mixture. You may get 2-ethyl and self-condensation. There are many things can happen. It is not so clean. But then what he did, he and his co-workers, they used a simple molecule called, what is this called? A pyrrolidine, a simple organic base, a secondary amine. You would remember this, and you should remember this molecule, this structure, the 5-member ring. Now, if you take this 5-member ring with the nitrogen, it would form a bond with the carbonyl, form an imine, and it forms enamine, which is in the tautomerism type. It is in the equilibrium. And now, thus I've shown you here, this double bond acting as a nucleophile, it pushes there, and the lone pair is pushing here. You get this, you can see that iminium ion, and this is enamine, en and amine, enamine. Enamine attacks the Michael acceptor, and you would end up in getting one-sided product, because it is not here. You may not get so selectively. It is not so enantiomer specific, enantiomer selective, but you will not get other products, because the pyrrolidine itself is not enantiomer pure, but then it is giving you a kind of specificity, because the enamine is one-sided, means double bond will not form from both sides, because it can, but it is symmetric in nature. If I put a methyl group, then it becomes little specific. If this molecule is symmetric, hence there is no question of enantiomer selectivity or specificity. But this became a very, very important founding stone, and many people, even many people use this idea. But then comes a very, very seminal or interesting work, but it created a lot of enigma, and that is nothing but Hajos-Parrish Eder-Sauer white shirt reaction. You may get confused with this reaction name, but don't get confused. Remember, Hajos and Parrish use this. You can see this kind of molecules where you have a diketone in a 5-member ring and a ketone, and he used for the first time proline, a chiral amino acid, L-proline. This is the first interesting, significant work pre-organocatalysis area. And then what he did, their group, they showed that it is forming a corresponding cyclic molecule. You can see this is very useful intermediate for the steroid synthesis, very useful precursor. And then he patented this technique. And somewhere around the same time, the Eider and the Sauer and the white shirt also published a similar work. And then this was named as Hajos-Parrish Eider-Sauer white shirt reaction. Why did not become so popular? Because those days they did not understand the mechanism in particular. Many models were given for the mechanism. The Hajos-Parrish proposed a mechanism. Agami and other scientists proposed another mechanism. Eider and Sauer, and our own Indian great chemist, organic chemist called Professor Swaminathan from Madras University, also worked on the proline in the year 1999, and he proposed another mechanistic model. And he happens to be my academic grandfather. He is my supervisor of my PhD supervisor. And also, this is something very interesting, right? Swaminathan also proposed. There were many models. There was not clear understanding what exactly happens, how it happens, and the number of whether hours or the time taken for the molecule synthesis. I think somehow it shrouded in the mystery, almost like it took 3 decades to understand this Hajos-Eder-Sauer white shirt reaction. This led to enigma, and its exact mechanism was kind of, as I told you, was in mystery. And then, interestingly, there comes a person called Carlos Barbas III. And this Carlos Barbas, he's a late Carlos Barbas, very, very eminent chemist, or you can say a great scientist. Wish he could have been there now, given it would have been an interesting part of the game. So he was working a lot on the aldolase and the antibodies. He was very, very interested in a lot of things, and he made the artificial antibodies. We know what is antibodies all about. Antibody binds to virus or large proteins, and then or the antigen it binds and then elicits the immune response. All of us know that, but it doesn't catalyze the reaction so easily like an enzyme, isn't it? Now what he did, he and his group made aldolase catalytic antibody. He called it catalytic because he expected that it would catalyze a reaction. And Benjamin List was there in the same lab as a very short time for the postdoc. And the Benjamin List also worked on the catalytic antibody. And then they did the first reaction of this kind of, the using the catalytic antibody. And then they did the Robinson annihilation type via iminium-enamine pathway. They called it iminium-enamine pathway. And they thought it works like a Hajost-Parrish reaction. And then they did some more. Carlos Barbas published few more. And then Benjamin List had a very vast experience working with the catalytic antibody. And I have shown here enzyme here, catalytic antibody. And I have shown, zoom the picture here, the most important part, the two molecules, let's say two amino acids. He thought, they thought this is not necessary to catalyze the reaction. You need entire antibody. Of course, you need it, entire enzyme. The catalytic site or active site can do the reaction. Some of you who have studied the biochemistry or medicinal chemistry, you might have studied the catalytic triad. Three amino acids can come together, can do a magic, right? So exactly, three amino acids are enough if they are on the active side. Same way, here he thought, not necessarily you need entire antibody. Is it possible to work with only one amino acid or two amino acids? Can that drive the reaction further for the enantioselective selective version? And here comes Benjamin List. Benjamin List thought that let me try a simple aldol reaction. And why he was inspired by this? Because Mother Nature has aldolase enzyme. There are two types of aldolases, class 1 aldolase and class 2 aldolase. The class 1 aldolase enzyme, class 1 aldolases utilizes enamine type mechanism. The lysine is there and it binds to ketone, and then things go very smoothly. And you might have studied even keto-glutaric acid in the biosynthetic pathway of amino acids, isn't it? But here, the aldolase does the aldol reaction using an enamine E type reaction. And the class 2 aldolases use the metal cofactor, for example, zinc cofactor. At that time, metal catalysis was a peak. Shibasaki, Watanabe, they published a lot on the metal catalysis following or mimicking the aldolase 2. Benjamin List and the Barbers had worked a lot on the antibody, aldolase antibody, as I told you. He thought possibly a one amino acid can do the same job because Hajost-Parrish had done something. That's what I told you. Past is important. History is important. You need to read the publications which have appeared much before your own research idea. So what he does, usually if you start off with a ketone and an aldehyde, if you treat that under the basic condition or acidic condition, you would get an aldol. But you would get the two mixtures, isn't it? Equal proportion, racemic mixture, 50-50. Even though I have shown the chiral carbon here, chiral carbon can exist in two enantiomers, hence they are racemic mixtures, hence because they are mirror images, 50-50. But our aim is to make it one single enantiomer. What he did, he used the proline. If he used proline, he ended up in getting, though it was not really highly encouraging, but one of the reaction, one of the substrates, you can see the two substrates like acetone and this aldehyde I've shown here, that gave almost like 96% EE, 97% E. Isn't it remarkable? And you did not get the another product, another isomer. So this is something so beautiful. This was the founding stone. Now you made a simple aldol reaction using a simple unit, single unit called proline, L amino acid, organic molecule, very small, hence not so much big in atomic number and atomic mass. And it is quite sustainable because it is natural, comes from the chiral pool. And you are getting 96% EE. And they screen many things and they try to optimize the reaction condition very well. And they observed variable enantiomer selectivity. But then this became a stepping stone. Why? Why this selectivity comes into picture, even though there is no enzyme pocket? And what kind of pocket is all about? You see over here, very simple term. I hope you will all understand that, as I told you, if this acetone reacts with the proline, it would form the iminium, and it forms the enamine. This is in ketoenol tautomerism because ammonium ion will pull the electron towards itself because it has lost its electron lone pair. nitrogen is more electronegative than the carbon, hence nitrogen will pull the electrons towards itself, and then you expect the enamine. Now, why it has happened enamine? Why it has become enamine? Because of the ammonium ion, now the CH3's pK has reduced drastically. Hence, this proton can be lost very easily, and hence it became the enamine. You can also write as a negative charge, that's not an issue, but then even like iminium ion carboxylate, and it becomes the enolate. Anyway, I think then if you see this is the product. Now, exactly here, if proline is binding, proline itself is chiral in nature, and the L-proline one-handedness, D-proline other-handed, right? So I have taken one proline here, for example. You can see over here, this proline is, oxygen is here, it is binding because this enamine has formed now, and it is a weak interaction now. Enamine is nucleophilic in nature, and the carbonyl of the aldehyde, carbons of the carbonyl aldehyde, carbon of the carbonyl group or an aldehyde is electrophilic in nature. Remember, acetone's carbon is also electrophilic, but when it reacts with the amine, it becomes enamine, and this carbon became nucleophilic. So now you can see a kind of chair-like structure here. Oxygen is binding to hydrogen. This carboxylic group, this is becoming weak. This bond is becoming weak, and this bond is forming, and this carbon bond is forming, and then you can see that finally it forms a bond. And then what happens? The proton is lost as well as proton is gained. Now, this is something very interesting. Proline's proton can be lost, it can gain. Lone pair is lost, it can gain. Hence, it is like acting like a bank. So this is very essential, right? So then he called it as microaldolase in this paper, a seminal paper in JACS 2000. He called it as, and you can see Barbus is there. And this beautiful work led to a lot of other work. So they start screening the solvent, they start screening the substrate scope, they worked on a lot of other work. Benjamin List independently started his career. He started working on the Michael reaction, Michael addition, Manich reaction, multi-component reactions, and many other things. So now come to the second part of the organocatalysis, that is the Nobel Prize for the David Macmillan. And what is so special about David Macmillan's work? Discovery of highly enantioselective organocatalytic Diels-Alder reaction. I hope you remember previously I told you enamine means I told you enamine, right? Here it is iminium. So what did he do? He did the simple Diels-Alder reaction. And what is so special about Diels-Alder reaction? All of us know that. Diels-Alder reaction is very interesting. It can also undergo retro-Diels-Alder reaction. But then Diels-Alder reaction at his time, during those days, mostly they were dependent on metal catalysis. And the first seminal paper appeared in the year 2000. The first organic molecule was used to catalyze this Diels-Alder reaction selectively, stereoselectively. So this is something very interesting. What is that? Just let us see this. If you take unsaturated aldehyde, and if I start uh, treating the aldehyde with the diene and an aldehyde, and in the presence of 20 mole percent of the catalyst, I will show you catalyst, you would end up in getting the product. But in the absence of the catalyst, you would get the mirror images. So now what is that catalyst? It's called imidazoledinone, which is developed by Macmillan and his group. And I will explain that about that catalyst. Now, what did they do? Beautifully, you can see only one isomer was formed. And so endo, you know this? I think many senior students and the other members, they know that Diels-Alder reaction. It's very interesting. It usually gives endo product in large quantity compared to the exo product. Usually, it's not. It's slightly favoring towards the endo products because of the secondary orbital interaction and something else you might have studied in physical organic chemistry. But then when he specifically did this reaction, you can see that endo was more usually, but 90% enantiomeric excess was there. One single almost exclusively. And what is so special about spatial selectivity? What is so special? You can see that in this paper, 2000 again, he coined the word called organocatalysis. I have highlighted in yellow. This is the first time David Macmillan used the word organocatalysis. It never existed, this word. He coined the term organocatalysis, and sometimes Macmillan himself says, and he said, sometimes giving a catchy word can make a huge difference. Though there were some reactions, though Hajos-Parrish reaction shrouded in the mystery, but then the whole giving new word, new face, it changed the game. So organocatalytic reaction became a foundation stone as a third pillar, because now he did a beautiful molecule called imidazolinone. How it's derived, you can see phenylalanine. If you see here, phenylalanine amino acid, and he made this cyclic system with a secondary amine again, just like a proline. And if you treat that secondary amine with an aldehyde, it will form an iminium ion. Okay, it is not imine in amine, it is iminium because it has a positive charge. Hence, this iminium ion is acting as a Lewis acid, and also their aim was to have the kinetic reactivity such that ligand exchange will take place faster, and then the turnover frequency will increase, and it would be a better catalyst. And what is so special about this? And he called it as LUMO activation, lowest unoccupied molecular orbital. I will not get into detail. What is LUMO activation? Because of this intermediate, the activation energy barrier lower. If you just simply take aldehyde, it would be a little higher, whereas this intermediate, you can see because of the imidazolinone part, its activation energy barrier lower. And because of that, reaction was driven faster. Reaction was very selective because of the chiral pocket. Chiral pocket induced the chirality, and you got one single enantiomer. And they showed here the phase. You can see the phenyl group is above. You can see that. And the methyl group, one is above, one is below. And you can see the whole system is like a pocket. Hence, you can see this cyclohexide, this diene can approach only from the psi phase or the C phase. Right? It cannot approach from both the phases. If that happens, you would get one molecule, though you have a competition, major minor for exo-endo, but then enantiomer selectivity was pretty high. So there are exceptions. Mother Nature has very interestingly deals aldolase enzyme too. Alternaria serrani, a bacterium. Sometimes it gives 50-50. This is something very interesting when I don't know that. And then I will not be able to do justice because of this founding platform, organocatalysis, third pillar. You got a big stability now for the bar stool. Third catalysis started, third type of catalysis. It kind of constitutionalized it, or it became conceptualized the area. Now many people in the same time started working. I will not be able to do justice because it's such a vast field. I just in hurry I've taken only few names. Jorgensen, almost similar time, he worked on the organocatalysis. Hayashi worked with the Hayashi's catalysis. Sorry, I think I missed the name here. Maroka did the beautiful phase transfer catalyst. Remember one thing, organocatalysis became a huge field, and it became covalent organocatalysis, non-covalent organocatalysis. Means weak interaction can drive the reaction, not necessarily covalent bond like in amine or iminium. Even the simple hydrogen bond can pull the molecules together, stitch the molecules together, bring them closer, make the chiral pocket. That is called a non-covalent organocatalysis. And the chiral phase transfer catalysts, Morocco did a fantastic job. Then Berkesel used the weak interactions. Dieter Endres used the, Romp and Samp used the organic molecule, again, amine-derived molecules. And the Kian Hawk did the beautiful computation calculation of the mechanistic understanding, many more. Jacobson, the Harvard, the Jacobson, you might be knowing the Jacobson's oxidation. Jacobson did a beautiful work, and he came up with the thiourea based catalyst, that is a non-covalent catalysis. Then many, I think I'm missing. I'm sorry that I could have done the justice, because if I would had a time. But from Indian own perspective, from our own India, there are many people, almost 15, 20 or more than people from last 15, 20 years. They have been working on organocatalysis. I told you Swaminathan, great Swaminathan, one of the earliest to work on the organocatalysis using the proline. But then Professor Vinod Singh came up with a beautiful catalyst, for the organocatalyst. And the Raval from the USA again did the squaramide-based beautiful organocatalyst. And all of them worked a lot to make organocatalysis what it is today. And Professor Basavaya from Central Hyderabad, Professor Ramachari did a seminal work too. Professor Shantanu Mukherjee is my good friend from IISER Bangalore. He worked with Benjamin Lace. And the Professor Biju worked on he's working on the NSC-based carbonocatalysis. Many PAN, there are many people. I might not be doing justice, but then handful of people are doing the organocatalysis. They have contributed a lot. And you can see very quickly, and I should stop here. You can see Breslow. He's one of the earliest. I think Biju works on NSC catalysis, as I said. This became the stepping stone for N-heterocyclic carbenes. And even though this is not the proline-based organocatalysis, but this is the organic molecule-based catalysis called, which is like Ampulung idea. It started somewhere around there, and then the Bender, then many of Hajos Parosh, I told you, Sibak, worked a lot on the Ampulong and conceptualization, means the changing or reversing the polarity, and then the Macmillan, Barbers, and the Benjamin List, and then Hayashi, I told you, and now the organocatalysis is going towards the more sustainable, doing the reaction in water. So what I did, I'm a minuscule particle in the vast ocean of organocatalysis. I would not take much time. We contribute with a good, we contribute very, very little in the vast ocean like a small fish, and credit goes to my students. So we just showed that there is an adverse effect of higher catalyst loading and longer reaction time on the enantiomer selectivity. So Benjamin List and co-workers had published almost like 20 years ago a 3-component reaction, exactly this reaction, but then there was no enantiomer selectivity. It was a disastrous, just 5% enantiomer selectivity was there. Even the Barbers tried that, but then almost all of them got the racemic mixture. We worked very hard. I must say that Tushar Kopde, my student, Dr. Tushar Kopde, he did a lot of work to come up with an idea, and we made sure that we can make enantiomer selective version, and we use the bifunctional amino catalyst here. And as I told, we are only contributing very little. And what is so special now? Why we have to do organocatalysis? Remember one thing, 2019, a periodic table appeared, a new periodic table, I must say. It's not, don't take me in that way. New periodic table in the sense, metals which are vanishing, metals which are scarce. So you can see green, yellow, and orange color. Many transition metal and metals are disappearing because we are digging from the earth crust. So hence, we have to make the life more sustainable. We have to make sure that molecules react with each other more sustainable manner. We need to consume less energy. We need to make sure that our sustainable reaction towards the greener globe will lead to the progress of the society or the whole mankind or humankind. So what is so great about organocatalysis? It's benign. One of the greatest potential of organocatalysis is that it uses naturally occurring amino acids and derived molecules and making environmentally friendly, and it is used as an industrial advantage, especially many pharmaceutical companies, agrochemical companies, they have to make these molecules using organocatalytic pathway to get one single enantiomer. Now you understand thalidomide and many other drugs. No pre-activation. You can see directly we took the aldehydes and the other reactive partners, ketones. You don't need to protect and deprotect it. That means you're saving the molecule, saving the energy. You are not wasting the atoms. You're not wasting the molecules. You are not throwing into the garbage. So hence, you are going towards the greener globe as much as possible. Though many chiral metal complexes lead to the high enantiomer selectivity, but the organocatalyst gives access to highly enantiomer pure molecules under metal-free condition. Why it is important? Because pharmaceutical industries, they make a lot of compounds. They use the metals, they use the metal complexes. These metals would leach, and finally, when the drug goes to the market, it should be metal-free in the ppm level. It should be free from the metals, right? Hence, if you avoid the metal, it would be great, isn't it? So now, as I told you, reaction can be done in an environmentally friendly way, and friendly solvents can be used. Environmentally friendly solvents or green solvent can be used. Open air condition, no dry condition necessary, moisture free, moisture is not an issue. No heating is required. That means you're saving energy. No cooling is required. Exceptions are there, but then mostly amino acids are like a food supplements, right? And you can substitute with the toxic metals. Another tantalizing aspect of the research is that it raises the possibility of prebiotic role of proline. Did the proline induce the chirality or the enantiomer selectivity in other amino acid too? I think this is something interesting, right? That's what the Carlos Barbers talked about. And application in the industry, I will not dwell. So many molecules have been synthesized using the organocatalytic step or a pathway. You can say potential uricosuric, this is a diuretic agent, estrogen receptor for the beta modulators, immunosuppressants have been synthesized. There are many, many. Final conclusions, great potential in industrial application, especially making environmentally friendly processes towards a green globe, towards a progressive society, so that we all can live for longer. No pre-activation, I've already mentioned that. High enantiomer selectivity, higher yield too, more sustainable chemistry, access to both the enantiomers, right? So if you can recall the enzyme reaction, you have only one type of enzyme, one R or S means one-handedness is an enzyme, then you would get only one enantiomer. But then you have R proline, L S proline, or L proline, D proline, or R isomer, D isomer, you can make as a chiral catalyst, and you can get both the enantiomer. This is a great strength too, right? I mean, it's very interesting compared to Mother Nature too. But then, what are the challenges? We need to reduce the catalyst loading. There are many chemists, they have been working on that, and we showed that sometimes higher catalyst loading and the longer reaction time can be detrimental. More is not merrier. We have already shown that. Need some more efforts to mimic the Mother Nature in more closely, so that we can do the reaction in water. So hence it is almost close to Mother Nature. We need to come up with the more substrate scope, more catalyst, more efficiency towards a greener globe. And thanks to all my students who contributed a lot to a bit of organocatalysis from our group. And I'm really thankful to all my students. Tushar, Prakash, who worked a lot on organocatalysis before Prakash, and Amar, to some extent, they touched upon that. And I thank everyone. And I'll stop at the end of the day with a simple quote again. Simplicity in character, in manner, in style, in all things. The supreme excellence is a simplicity. That's what the Mother Nature believes, and it does. Whether it's a Hobson's choice or Mother Nature was wise enough to do. So let us mimic her. Let us go towards her to the great greener globe. Thanks once again. Thank you. I hope you can hear me. Am I audible to all of you? So one of you can
Yes.
speak. Yeah, yeah.
Yes, sir. Yeah, you're audible.
Sorry. Yeah, I think there is some questions there I can see, but I am not able to read. Can anybody see that? Okay, I think, yeah. I don't know if someone can read it out, otherwise I should read. Dear sir, I have a question. How do we resolve or separate enantiomers? Very good. I think I did not touch upon that. One of the fields of getting a single enantiomer is starting from the racemic mixture. You can start off with the racemic mixture, 50-50, and you can go for the resolution, kinetic resolution. Again, it's a bigger field, kinetic, dynamic resolution. There are many subdivisions are there again. So what you do is, you will, so simple way I can say that I will not talk about the resolution in depth, but let us say, for example, one of the simplest ways, for example, you have an enantiomer. Enantiomers cannot be separated, or it cannot be separable on the column chromatography. Normal column you cannot separate. Even in proton enamel, you can't see enantiomer. If it is like one chiral carbon is here, you can't see two peaks for the two 50-50 two isomers, because enantiomers are mirror images. The peaks will not be different. Whereas diastereomers, you can see different peaks, diastereomeric peaks. Now, one of the easiest ways, can I make a diastereomer and separate? For example, I would take an enantiomer, which may be having a functional group, which can be hooked onto another chiral molecule covalently. And now what happens? It is going to be now diastereomer, because the another molecule has a chiral carbon, and the molecules to be separated, enantiomers or the two isomers to be separated has chiral carbon, but they are enantiomers. I will bind them, now become diastereomers. Diastereomers can be separated, and now you have separated them out. It is a simple way, means you made the diastereomic mixture. Same way you can do enzymatic resolution and many more things. Okay, now why are we focusing more on the asymmetric synthesis instead of separation of enantiomers? I think this is a connected question only from the Garvit. Okay, Garvit, nice to hear from you, Garvit. So Garvit, resolution means you start off from the mixture, racemic mixture, right? That means you are dependent on the existing compounds. First point. Now, do you have an existing compound as a racemic mixture? Then you need to separate that. That's called kinetic, or any resolution you do it. But then you would separate them, and one isomer will come out. Another one is like enriching the one isomer, right? See, another isomer is left behind. Again, for that, you have to go for that. But then that's not an issue. But the point is you have to spend time depending on the racemic mixture only. You can't come up with the new molecule. You can't come up with the, let's say, new drug is there. The medicinal chemist, they designed a new molecule. So now you need to synthesize single-handed molecule, means one pure enantiomer is better than synthesizing racemic mixture and spend again time and money and the labor to separate them out, isn't it? So any other questions? Same like we do protection and reproduction of functional groups. No, protection and reproduction is an extra burden, even though many a times it is unavoidable in organic synthesis. But you only think, for example, I have to protect a functional group because it is so reactive, and then I have to do another reaction at another site, and then I deprotect that protecting group because it was so reactive than the another functional group, and I had to mask its reactivity. It's like I'm tying you on a pole because you're so active person, because I want someone else to speak. So I will be closing your mouth and then I will be removing that so that you can speak. Means I do extra business. Means protect, deprotect. This includes labor time, efficiency is lost, atom efficiency is lost, a lot of wastage generated, extra steps have been, like 2 steps have increased. Protection, reproduction. So there are problems, but I hope you understood the concept of organocatalysis. A simple organic molecule will do or drive the reaction towards a final product or the aimed product or a molecule in one single enantiomeric form. Sometimes you will get major minor. It's not 100% exclusively you will get it, but we would say that it is 90% above is really good. Then you can still crystallize them and you can get that. There are many methods, but not all of them are very easy. 100% yield versus EE. One is the EE and another one is the yield. EE means enantiomeric excess, or you can say enantiomeric ratio if you are comparing the two isomers. If one is measured in percentage with the other, then we say excess. Ratio means you're just seeing a ratio. One is higher, another one is shorter, means in the HPLC, or in the percentage wise, I'll say one is higher, another one is smaller. It's a ratio. So 100% yield is quantitative, yield may not be quantitative. That is the product amount starting from the starting material. If you go from the Avogadro number like millimoles and then the calculations, you'll get the percentage of the product. The EE is something to do with the enantiopurity. Even we can't claim 100% because we believe the most sensitive instrument like HPLC might not be sensible enough to see 100%. So hence, even though you may not see the peak, you may see only one single enantiomeric peak, but you may say it is almost quantitative, 100%, but we presume there may be such a small amount, it might not be appearing in the HPLC. Hence we almost call it quantitative. It may be 100% on paper, but we say that it is almost like 99.999. Hence we don't even call any dry solvent 100% dry. We say it is like 99.999, or you could say quantitative conversion, quantitative drying, you could say quantitative EE. I hope it's clear. Okay, won't this cause a problem if minor enantiomer is toxic? So if you know already one isomer is toxic, as I told you in thalidomide earlier, we did not know one isomer is toxic. Hence, unfortunately, a lot of people were born with the vestigial arms and the defected people were born, babies were born. That's so unfortunate, isn't it? That was a lack of understanding of science. Now, the beauty of science is it can make life and death a different ball game. It can try to save you. It can try to save people who are on the deathbed. At the end of the day, we may not be ultimate people to save everyone, but at least we can attempt to save someone. But if you don't know the enantiomer is toxic, then you have to synthesize and separate them, or you can synthesize exclusively and try for the studies, toxic studies, metabolic studies, and many other things, which exactly many academicians who are working in the field of medicinal chemistry or the large extent industry, pharma industry, they work very intensely to see the purity and the toxicity and its ill effect and the good effects.
Thank you so much. Any more questions? I'm ready to take.
Hello, sir.
Yes, yes, yes.
Sir, I would like to ask one question. So in the paper you showed, so
Okay,
your group.
you want me to go back?
No. Just
Okay, 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 okay.
clarification. So the paper you published in your group, of your group, you like you developed the organocatalyst you have made, right?
No. We did not develop the organocatalyst. This is a well-known organocatalyst, but we call
Okay.
it as a primary amine catalyst. See, um, as I told you that to begin with in 2000, proline-based organocatalysis started. Then slowly it became a foundation for the asymmetric catalysis using organic molecule. But then many molecules were not driven by proline or
Mm-hmm.
amino acids. Then what happened is like people also looked for the natural molecules like cinchona alkaloids or quinines. These are all the organic molecules which are in the nature, and people means many researchers have contributed a lot on the other type of organocatalysis. I told you the non-covalent organocatalysis means a
Correct.
weak interactions. So now
Yes.
the primary amine catalyst here, this is a bifunctional amine catalyst. You can see over here, tertiary amine is there and the
Hmm.
primary amine is there. Now this is
Yes.
called bifunctional one. It can do a job, means like, it will interact with the weak interaction. It would pull down, one is going to bind, let's say covalently. Another one is kind of binding because it's forming a quaternary ammonium. You understand my point? Like
Yes.
thiourea
Yes.
is a non-covalent catalysis.
Correct.
So here you have an amine which can be covalent. So this is called a bifunctional catalyst. So
Yes.
what we
Okay.
did, so I think I give a lot of credit to my students. What we did, it's a very simple one. The Benjamin List and co-workers had published almost 20 years ago exact same reaction,
Mm-hmm.
three component reaction in the
Okay.
Synlect, and they got the very good diastereo selectivity, but the enhancer selectivity was disastrous. It was just 5%. And the
Okay.
Carlos Barbas also had tried, and many others tried, but they were all getting racemic mixture because they used the proline as a catalyst. So
Okay.
what we did, we screened many catalysts, the known catalysts. We did not develop, but what
Mm-hmm.
happened is for us also we are getting racemic mixture.
Okay.
So then what we understood is the catalyst, like for example, primary amine catalyst like this synchrona, this catalyst, it it is acting as a catalyst, acting as a base, both, right?
Okay.
So
Okay.
now it is acting as a catalyst to drive the reaction. Once the product forms, base is there, because we are using, let's say, excess percentage like 10 mole percent or 20 mole percent, and the base is doing the retroaldol reaction or retromichael reaction kind of thing, right?
Okay.
Retromichael
Okay.
reaction.
Okay.
So now if that happens, you are getting the racemic mixture again. And the
Mm-hmm.
Tushar worked so very patiently that we did HPLC studies, gradual studies, and we saw that within few hours it is highly enantiomer, 99%. By overnight it is becoming racemic. Means if you leave it for a long time, it is becoming racemic. Then
Oh.
we did a lot of studies
Mm-hmm.
and NMR studies, variable temperature NMR
Okay.
studies, many other
Okay.
things, and we understood that more is not merrier. You cannot use excess catalyst all the time. And proline also
Mm-hmm.
they use excess, and they were getting racemic mixture. Here we
Mm-hmm.
understood one beautiful concept that higher catalyst loading is not good for all the time, because
Okay.
we believe if you put higher catalyst loading,
Mm-hmm.
it
Mm-hmm.
will drive the reaction faster. And if you leave
Okay.
the reaction for longer time, you would
Mm.
get better energy selectivity. But then we understood one thing very interestingly. Albert Burkessel, I told you, Albert Burkessel had also shown something similar, but this is a very seldom in the literature. Very seldom
Okay.
in the literature, that
Okay.
adverse effect of higher catalyst loading as well as
Mm.
simultaneously longer reaction time. We did something a small contribution, nothing great,
Mm-hmm.
but I feel happy that after 20 years we got the enantio selective
Pure.
Benjamin
Okay. Yeah.
list
Okay.
component reaction. We called
Okay.
them at the list reaction.
Yeah.
Thank you,
So,
Kovi.
so just one more point. So, knowing the catalyst have you have used and the literature as well. So, can I devise a similar catalyst which gives me the other enantiomer? Like knowing that okay, this
Yes,
works
yes,
to
yes,
make
yes. You are right.
a particular enantiomer. Then I would like to explore the other possibility because the
You
other
are
phase
right.
will be going to be logged.
You are right. Now the strength comes from the organic synthesis. For example, there are molecules which are available in the chiral pool, means the mother nature has.
you're using like amino acid, or you are just isolating somewhere and synthesizing further. So here comes a strength of organic synthesis. If the molecule is available in the nature, starting from the scratch, if you have to synthesize, then you have to be very, very smart, and you have to synthesize from the scratch and make your own molecule. For example, Macmillan used the chiral pool, that proline, he used the phenylalanine, and he made the imidazolidinone. Means he started off with the phenylalanine, which is available in the nature or available from the nature. But then certain times you don't have everything in the nature. You want to build your own, starting from the achiral system. So you have to use somewhere the chiral inducing molecule. Either I have to use enzyme, I have to use the metal complexes, chiral metal complexes, or I can use the chiral organic molecule to drive the reaction towards another reaction towards the getting an enantiomer product. So now the strength comes from the synthesis, right? Like that's why we have to remember Woodward, E.J. Corey. E.J. Corey is also to some extent my academic grandfather, because my PhD supervisor worked with E.J. Corey. So they all contributed significantly towards the organic synthesis.
Yeah. Thank you, sir. Thank you.
Thanks. Thank you, Ankur. Yeah, shall I come out of this presentation?
Okay, so does anyone else have any more questions?
Thank you so much.
Oh, I think Gavit has a question, sir.
Who, Garvit?
Yeah,
Okay,
Gavit.
Yes, sir.
Yeah, Garvit, how are you?
So fine.
Yes, Garvit.
Sir, so does the chirality of the enzyme also matter when we do the asymmetric synthesis? Like the D enzyme would give me one enantiomer and the L enzyme would give me the other enantiomer.
Yeah, so
Does
exactly
that
that
happen?
I mentioned. For example, most of us are made up of L amino acids, and L amino acids will make the protein or enzyme based on the L amino acids sequence which is inducing the chirality. For example, the famous Ramachandran plot, if you read it in the biochemistry textbooks, like helicity, how would Ramachandran plot talk about which quadrant which will fall, and then beauty that how L amino acid is inducing the chirality in the helices, because the hydrogen bonding, like knitting together the molecules, how they come closer. This is all beauty, right? So now L amino acid enzyme would give one L amino acid derived enzymes would give one particular enantiomer. Like if you take the D amino acid derived enzyme would give another enantiomer. Exactly. Same way, if I take, let us say, L-proline, it'll give one isomer, one enantiomer, and the D-proline would give me another enantiomer. You're right, Garvit. But then the point is, nature may not make all kind of enzymes, right? Mostly it is L amino acid derived. Exceptions are there where some of the bacteria, they use a D amino acid sequence and they make D enzymes.
Oh, okay, sir. And also, sir, I have also written this question on the chat, but about heavy metal toxicity.
Yes.
So, if I extract my enzyme after the reaction is completed, how will that cause heavy metal toxicity?
No. The heavy metal toxicity is not coming from the enzymes. So I think you might have missed it. Like enzymes sometimes catalyze a reaction using the cofactor. For example, I told you class 2
Yes,
aldolase,
sir.
which has a
So
zinc
I meant
cofactor.
metal catalyst. I
Yes.
meant metal catalyst only.
Okay. Metal catalysis, but there's something called, let us say, I use the metal complex, right? Metal complex, when we're using, metal complexes have chiral ligands, and the metal is bound by chiral ligands, or chiral ligands are bound to metal. So now what do? You do the reaction in the homogeneous catalytic pathway or the heterogeneous catalytic pathway. So if you're doing the homogeneous catalytic pathway, where the metal catalyst is dissolved in the solvent, and then the product is formed, and then you need to filter it, or if it is not even dissolving, you have to filter that, and you do column chromatography, right? Or you have to purify that. So now small percentage of the metal which is coming out of the ligand as a metal salt, which is metal salt, even if you think that metal salt should not be soluble in organic solvent, but there is something called principle, ether dissolves in water, water dissolves in ether. You know that, solubility coefficient, all these things, a very, very small product can always dissolve. For example, when I take a toluene, why do we dry the solvent toluene? Because water is there. But technically, if I take water and toluene, it is not soluble, right? You say that the toluene layer is above and the water is below. But then if you take the toluene bottle, the micro amount of water is everywhere, and hence it is not dry, it is not anhydrous. It's exactly the same way. Metal can leach in a very, very small percentage that we may not be able to see in round bottom flask, but then that is going along with the compound even after the purity, even after the purification in the ppm level or ppb level. If it is there, it can be risky, right? If it is in some ppm, 100 ppm, 200 ppm, let us say, if it is heavy metal, it can be toxic to the person who is consuming the pill. Hence, it's not that it will always cause a problem. Pharmaceutical companies, they take extreme care and extreme caution to purify, but then it can go wrong sometime, or it can leach, or I mean it can come out, then it can cause. For example, there was a noodles issue, you remember that certain heavy metal
Yes,
toxicity is
sir.
coming from where? That is because of the particular metal was used in all the steps. So for the hydrogenation possibly, isn't it? So it can leach, or it can come out, and then it can lead to a problem. Hence, companies make sure that it is ppm level, extremely tolerable level. And all of you have to be careful too. Let us say you're eating a fish from a river bed which is loaded with chemicals. You never know, you're eating the fish with the methyl mercury poison. It may be in a low percentage, but you are having the dose of methyl mercury or the mercury. Or you have growing the vegetables where the arsenic is running in the water. Maybe vegetables may be absorbing some amount of arsenic too. So hence, as I said, our greatest key driving reaction towards the sustainability is, if possible, to save the world by utilizing the metals as less as possible. However, metal complexes have done a great job, and still we are using it. We are not 100% free from metal complexes. We are still dependent on them. But in case if we can come up with a more robust, more solid, more um, uh, organic, which is just like a nature, then it would be great, isn't it? Because we are digging the mother nature, mother earth, to extract the metals from the ores, and it is not so abundant. Thank you so much, Garvit.
Okay, sir. And in all metal complexes don't have heavy metals, right? Some
Sorry,
metal complexes may even have calcium, magnesium, and so on.
sorry. What
So,
all metal complexes are what?
so all metal complex don't have heavy metals, right?
No.
Some metal
Yeah, you
complex.
are right. You are right. You are right. It is not necessary that all metal complexes are having high metals, heavy metals. For example, I told you the Shibasaki and the Watanabe, they worked on the metal complexes to drive this reaction, right? Shibasaki used the, I think, lanthanum based, but there are others use the other metals. But then now what metal complexes you're using for what specific purpose? What is the strength of the heavy metals? For example, heavy metals, not necessarily I'm talking about very heavy metals. Even if you think of, let us say, palladium, rhodium, ruthenium, why are they so specific, Garvit, on the others? Because they have an ability to have a variable oxidation state, right? They can change their oxidation state very easily. They're like a electron sink, electron bank. So alkaline earth metal or alkali metals may not have the same ability to change just like the heavy metals, means this palladium. If you see coupling reactions, then which Nobel Prizes have gone for that, Suzuki coupling, let's say, like Heck reaction, Negishi coupling, Heck coupling. So you see beauty that palladium is a major factor there. Palladium is a central metal. Even though transmetallation takes place in the case of Suzuki and the Negishi, Heck doesn't have transmetallation. Now, almost all the organic counterpart from the boron or the zinc or the magnesium or the tin, they transfer onto the palladium. Now comes the electronegativity part, carbon, palladium's nature. So electronegativity of carbon and the palladium's electronegativity, palladium's variable electronic states. So a lot of things matter, Garvit. A lot of interesting things are there. Hence, it becomes a very much of a celebrity or more of a focus. Hence, they do a lot of interesting reactions.
Okay, thank you, sir.
Thanks, Garvit. Okay, I'll stop sharing the slide now. Okay.
I'm assuming there are no more questions. Okay.
Thank you so much once again. Thanks, club and the organizers. I hope I did do a justice. I just was feel I might have missed few scientists' name, and I also forgot to show the I think slides where I have used the different links and the website that I've used. Sorry, I can share with you later. I have used a lot of information from the books, Google, YouTube, and many places, and to learn. And of course, I work on that. I thank everyone uh, for making this happen.
Thanks a lot, sir, for the wonderful talk. I think it was wonderful. I don't have any other words. Um, and thank you for giving so much time today for it.
It's
Even
my
though
pleasure.